Any questions before I get started today on some functions? No? Do I hear someone's mic turning on? Is there a question? Okay. Haven't heard or read anything. If someone's trying to speak, you'll have to work a little harder because I don't know what you're saying. Let's talk about some functions. Can anyone remind me of something we talked about 2 days ago about functions? What's something interesting about functions? Yeah, these are some good things. So some things to remember. So yeah, one is that the range is a subset of the codomain. And if I think of my functions as arrows pointing from one set to another, then the range is the subset of things that get hit by arrows, right? Oh, shoot. And then the second thing is that, so the pre-image has a unique image is perhaps a slightly different way from what I'd say, but I'd say that every element in the domain has a unique image. So every element in the domain has a unique image. Technically, I want to point out the following kind of picture. Let's say I have A, B, and C, and then I have 1 point or like 2 points over here. So like 1 and 2. And let's say A maps to 1, B maps to 1, and C maps to 1. Then what is the pre-image? Oh, is there a question? Yes, there is a midterm on Friday. That's correct. This Friday, there's a midterm at the same time as usual. That is class time. Yep. Okay, so technically, the pre-image of 1 is the collection of all elements that hit 1. So the pre-image of 1 is the set A, B, C, and the pre-image of 2 is empty. So every element of the pre-image has a unique image, but the pre-image technically is like a set inside the domain. Follow-up question in that case, will functions be on the exam? Yes, functions will, but I can't ask you too much stuff about what I talk about today because that's kind of cruel and unusual punishment. So probably only the bare bones of what I talk today will be available, and you should think that mostly the questions will be from what we discussed Monday and prior to that. Okay, so here are some good things about functions. Any questions on my terminology or the ideas that I just presented here? It's not wrong to say that the pre-image of an element has a unique image, right? Because all of these elements get mapped to this one element. Yeah, that's right. So one thing that you cannot have in order to have a function is you cannot assign any element of your domain to more than one element of the codomain. So here's an example of a relation, A, B, C. A maps to 1, A also maps to 2, B maps to 1, C maps to 1. This is a relation, but not a function. Because A is being mapped to 2 separate things, so it doesn't have a unique image. That's correct. Any other questions? Okay, so let's carry on and let's discuss this next interesting thing. So here's a general idea. The set of functions f from A to B inherits structures from B. The codomain. And so what I mean is the following. So B is just a priori a set, right? And if I'm just talking about functions in their most general form, A and B are sets, and I'm just assigning elements of A to elements of B. But let's say that I take a set with additional structure. So let's say B is equal to either the integers or the real numbers or the complex numbers. So these things I can think of as sets with additional operations or sets with additional structure. Yes, a function is a special kind of relation. That's right. A function can be viewed as a special kind of relation. Here, the relation that I would assign to this picture with arrows is every pair that are joined by an arrow I add inside the relation. So here, this relation would be given by a comma 1, a comma 2, b comma 1, and then c comma 1. And this relation, which is a subset of the cross product of the two sets, is not a function because a appears on the list twice. Yeah, so you can think of a function as a special kind of relation with some special restrictions. Okay, so if we have an additional structure on our codomain, so here we can add or multiply in these sets. Right? We certainly don't have addition or multiplication defined for an arbitrary set. For instance, there's no reasonable way to add the members of our class. Like if we have our class being a set, there's no reasonable way that I can take two people in the class, add them, and produce another person in the class. But with integers or real numbers, we can add, and similarly multiplication. So the point is, if we have these additional structures on the codomain, we can kind of, functions can inherit those properties. That is, let f map from any set A to Z, for instance. And whatever I say for Z will also hold for the real numbers and the complex numbers. Is there an even more general set that includes real and complex? Yes, there's a space called the quaternions, which includes as a subset both the real numbers and the complex numbers. There are a lot of generalizations that contain both the real numbers and the complex numbers. Another direction to generalize is something called a vector space, like, for instance, C2 or C3. But we're not going to get into those in this class. Okay, so we're going to take two functions from A to Z. So F1 is a map from our set A to Z to the integers, and F2 is a function from A to Z. And now my question for you is there a reasonable way for us to add functions? What should F1 plus F2 as a function be? Well, what you should do is you can produce an element f1 of A and then f2 of A separately, right? There's some element in Z, f1 of A, this is some integer, and f2 of A is also some integer. And since we're in the integers, we can add them, right? So the function f1 plus f2 So I'm now defining an addition on functions, should be the function that sends A to f1 of A plus f2 of A. Let me give an example. We have one function, let's call f1 from, I'll make it from z to z. This function is going to be given by x maps to x minus 1. And then f2 is going to be a function from z to z, which is given by x maps to x cubed plus 4x. How do I add these functions? f1 plus f2. What is this going to do to an integer?
Excuse me.
Bless you. X is going to be sent to
would be x minus 1 plus x cubed plus
exactly.
4x.
Perfect. It'll be mapped to exactly x minus 1 plus x cubed plus 4x. We can check this, very easily if we write out what these functions do. For instance, f1 of 0. What's f1 of 0?
-1.
-1. What is f2 of 0?
0.
It's 0. And we can check exactly what is f1 plus f2 of 0 when we define things in this way. Well, it's exactly -1. So what we've done here is we've defined an addition on the set of functions. And the way that you define the addition is you take your individual functions, you send an element A over to wherever it goes via the two functions, and then you add there inside Z, inside the integers. In general, I can have it doesn't, so I do need two functions from the same set from the same domain to the same codomain in order to try to do anything with functions. So I do need two functions from the same set to the same set. Stefano, do you understand this addition, or is there a question?
Yeah, no, it makes sense.
Cool. And of course, we can do the exact same thing with multiplication. As long as we're allowed to multiply inside the codomain, we can multiply functions. How should we define the multiplication of f1 times f2 of A? What should, if I know what f1 does to A, and I know what f2 does to A, and I can multiply inside the codomain, how should I define f1 times f2 as a function from A to Z? A should be mapped to what? It should be mapped to f1 of A times f2 of A. Exactly. This is like kind of the only thing it can possibly be. So f1 times f2, this new function that I've defined by multiplication of functions, is secretly nothing other than multiplying elements in the codomain. This should be equal to f1 of A times f2 of A. And we can do this same example. Since I can multiply in z, if I do this precise example, what is well, now I'm running out of space. Okay, I'm going to do it right over here. With this example, f1 being x maps to x minus 1 and x maps to x cubed plus 4x, what is f1 times f2? What does x get mapped to?
X minus 1 times x cubed plus 4x.
Yeah, exactly. X minus 1 times x cubed plus 4x. Really, all that I'm doing here is I'm showing that when your functions are described and when they have codomain the integers or the reals, then you can add and multiply functions as you know that you can. I'm just kind of warning you that this only holds when there are nice structures and properties on the codomain. If I have a function which maps from the integers to the members of this class, there's no good way of multiplying or adding those functions. Is that okay? Any questions? Cool. Okay, that was just a short note. Let's carry on to some very important properties. Injectivity and surjectivity, or one-to-one and onto, as in the terminology of the book. Okay, one-to-one and onto. I won't use this terminology, but, or at least I'll try to avoid it. So a function f from a to b is called one-to-one or injective. And I'll usually try to use the word injective. Yeah, I suppose that probably none of this can be on the next exam. Yeah. Okay. Function f from a to b is called one-to-one or injective if the following holds. If and only if f of a equaling f of b implies a is equal to b for all a and b inside a. Okay, so another thing that you should always think is that when you have an implication, you can always get an equivalent statement by taking the what? What is logically equivalent to an implication? Contrapositive, exactly. The contrapositive, and so you should think of this as being logically equivalent to this definition, is that if A is not equal to B, then that forces f of A to be different from f of B. In other words, different elements have different images. So an example, A, B, C, and then 1, 2, 3. And then I can make a function that sends A to 1, B to 1, and C to 3. And I can ask, is this an injective function? Yes, Catherine, that's the correct idea. Is this function injective? No, this function is not injective because it does not satisfy this property that f of a being equal to f of b implies a equals b, because here 1 is equal to f of a, and 1 is also equal to f of b. But so this clause or this hypothesis is true. F of a is equal to f of b for some a and b, but a is literally not equal to b in this picture. Two elements got sent to the same element, so this function is not injective. I think that's reasonably clear, right?
I'm confused on if
Okay.
if they got sent to the same element, how are they not equal?
I mean, there's always a function which sends every element of the domain to one element of the codomain. For instance, here's a nice example. People in this class and grades. I could assign everyone a B, right? This doesn't mean that the people in the class are all the same. It just means that they all got the same grade. They were all sent to the same place. This is still a perfectly good function, but it's not injective because several elements of the domain were sent to the same element of the codomain.
Okay, that makes a little bit more sense.
Right. So it's totally fine to send multiple elements of your domain to the same element of the codomain. That doesn't break any of the rules for function. Is this okay? But this would not be injective. Any questions on this? I have more examples, so. Here's another example. Let's define the map, which is called squaring from the integers to the integers, sending x to x squared. Is this injective? Why is this function not injective? Yeah, great. To show a function is not injective, we just need to produce a counterexample. So in this case, f of 1 is equal to 1 squared, which is equal to 1. Also, f of negative 1 is equal to 1 squared, which is equal to 1. So f of 1 is equal to f of negative 1, but 1 is not equal to negative 1. Thus, this function is not injective. Does this help a little bit more with this this notion? Great. And here we see that the domain and codomain versus, or the codomain versus range is really important. Let me define a new function, say f from z greater than or equal to 0 to z, sending x to x squared. Is this function injective? Yeah, this function is injective. And we can arrive at a proof of why this is injective pretty easily. This function is strictly increasing. we've cut off all the negatives, right? All the negatives are now gone. So I never run into this problem that I had when my domain was all of the integers. And then each integer will be sent to a distinct square because it's not possible to have two positive distinct integers which square to the same thing. So this is an injective function. There are questions on this? Essentially, I have removed the negative. So the issue here is that 1 and -1 go to the same thing. But in defining this new function, and it's new because the domain is different, I have cut off all of these negatives that were causing me issues. And so now this function's injective. Is this okay? Okay. One trick to kind of help prove whether something is injective or surjective is the following. So definition. This is of slightly less importance than what we've been doing, but it's still important. A function f from say z to z or g from r to r, these are going to be called increasing if a less than b implies f of a is less than or equal to f of b. We're going to call it strictly increasing if a less than b implies f of a is less than f of b. Similarly, decreasing if a is less than b implies f of a is greater than or equal to f of b, and strictly decreasing if a is less than b implies f of a is greater than f of b. And these should be pretty familiar definitions from calculus, right? When you're dealing always with functions from R to R. But these definitions make sense even when I'm working with the integers, right? We get some affirmations of some familiarity with these. Perfect. Glad to see it. So it turns out, and I'll have you prove this on your homework, that, so lemma, strictly increasing or strictly decreasing functions are injective. That's not true for increasing or decreasing functions. It's only the ones that are strict where you get injectivity. And there's a kind of picture for this, right? Let's consider the squaring function f from r to r, which squares everything. X maps to x squared. Well, if we look at the whole picture, it gives you a parabola. And this is several things. One, this is not injective. And two, it's not strictly increasing, and it's also not strictly decreasing. Not SI or SD, which is clear because on this interval, the function's decreasing, but then on this interval, it's increasing. So for instance, we can find contradictions to any of these statements, right? Here, for instance, if I put A is equal to -2 and B is equal to 1, then A is less than B, but f of A is 4. F of -2 is equal to 4, and f of B is equal to 1. So we see that this is certainly not an increasing function because A is less than B and f of A is greater than f of B. but it's also not decreasing or strictly decreasing. So none of these apply to this function, and moreover, it is not injective. However, if I restrict my domain, and if I consider f from r greater than or equal to 0 to r, x maps to x squared, then my graph looks like this. My only domain is the positive reals. And now my question is, on this new domain, is this function strictly increasing or strictly decreasing, or one of those?
Strictly increasing.
Yep, perfect. This is strictly increasing. And thus, it is injective. Also, if you're dealing with functions that have graphs, if you are dealing with functions with graphs, you can test injectivity by the horizontal line test. Right? The fact that this isn't injective, this x squared function, well, previously you said that's because f of -1 is equal to f of 1, and that's perfectly true. A way to see that visually is that there's a horizontal line at height 1, which intersects the graph at 2 points, both at -1 and 1 and at 1 and 1. In other words, -1 gets sent to 1, 1 gets sent to 1. That's the same thing as a horizontal line hitting the graph in 2 or more places, and that means that this function is not injective. One last comment on this. Obviously, this isn't the only thing that you should think of when you're thinking about whether or not a function is injective. The idea of a function being injective holds for arbitrary sets. And these definitions only hold for very special functions where the domain and the range both have orders on them, right? Here we're ordering the integers and we're ordering the reals. So if your function satisfies one of these properties, namely strictly increasing or strictly decreasing, then it's injective, but you shouldn't go around thinking that the idea of injectivity is captured by these things. The idea of injectivity is given by the definition that no two elements of the domain get sent to the same element of the codomain. Is this okay? Any questions here? Okay, cool. I mean, I think that injectivity, while we're doing it in a more formal and rigorous way than perhaps you've seen it before, it's still not an unfamiliar concept. And similarly with surjectivity, so onto or surjective. Plus, you all read ahead, so you all know what I'm talking about anyways. Definition. A function f from a to b is surjective if for all b in b, there exists an a in a, and f of a, or such that f of a is equal to b. Or in other words, everything in B gets hit by an element of A. Yet another way to say this is that a surjective function is a function for which the range is equal to the codomain. So for instance, A, B, C, and D. And here I've got a set 1, 2, 3. If I send A to 1 and I send B to 1 and I send C to 3 and I send D to 2, is this a surjective function?
Yes.
Yeah, this is surjective because for any element of the codomain, I can find at least one preimage. There are several for 1, either A or B works. The preimage of 2 is D, and the preimage of 3 is C. Everything in the codomain got hit by something from A, if we think of these arrows as these elements kind of hitting these targets. Is that a reasonable sort of notion? Any questions here? Well, let's play around with the same example because I've really got one example that I love and hold truly dear. No, I've got several, but here's an example. Let's think about f from z to z, which sends x to x minus 100. Is this function surjective? Yep, this function is surjective. So why is this function surjective? Well, let's pick any element in the codomain. Someone tell me an integer.
9.
42.
9, 57, and 42. We're going to do all of these. 9, 57, and 42. Okay, what I want is for each of these elements, I want to find a different integer such that that integer maps under this function to this integer. But what this function does is it takes your integer and subtracts 100. So is there an integer such that after subtracting 100, I get 9?
109.
Yeah, 109. So f of 109 is equal to 9. So I know that 9 is in the range. What about 57?
157.
Yeah, f of 157. If I subtract 100 from it, I will get 57. And how about 42?
142.
Exactly. 142 is an integer such that when I apply f to it, I subtract 100 for it, and I hit 42. Do you see how I could do this for any possible integer? Given any integer, b plus 100 is also an integer such that f of b plus 100 is equal to b plus 100 minus 100, right? Because that's what this function does. It takes in a number and it spits out that number minus 100, which is equal to b. Thus, b is hit by some integer under this function. Does this help show why this function is surjective? Actually, this is essentially the proof that this function is surjective. Questions here? Let's do another example. Let's do f from r to r given by x maps to x squared. Is this surjective? Right. This function is not surjective. Can someone tell me why?
Doesn't map to negative values.
Right, exactly. If I want to show a function is not surjective, all I need to do is to produce a counterexample. So a counterexample is that there does not exist a real number a such that a in the reals such that a squared is equal to -1. When you square numbers, when you square real numbers, they're always greater than or equal to 0, so this can never occur. In pictures, this looks like this. Here is my function, or the graph of my function x maps to x squared, and then here is a horizontal line at -1 that does not intersect the graph at all. So once again, this suggests a second horizontal line test as long as you have functions which have nice graphs, namely they're functions from the integers to the integers or functions from the reals to the reals, that says that if there's a horizontal line that you can draw that doesn't hit the graph, then it's not surjective. No, we hit irrationals with this function, definitely. There's some number called the square root of pi, which is a real number, such that f of square root of pi is equal to square root of pi squared, which is equal to pi, for instance. Square root of 2 also gets hit by this function, right? F of, I can take the square root of the square root of 2, right? Square root of the square root of 2, this is some real number. And then what happens is I square the square root of the square root of 2, which is equal to the square root of 2. So square root of 2 gets hit. No problem with irrationals here. Does 2 do what? Does 2 get hit? Yeah, absolutely. Square root of 2 is irrational, but still real. So square root of 2 is living inside this R, inside the domain. And so I can apply f to it and get 2. Right. They're still real numbers. They're irrational or maybe transcendental or whatever, but they're still real numbers, so I can still plug them into the function. Or if I wanted to do it another way, I could say there is a line here at 2, such that when I draw the horizontal line at height 2, it'll still intersect this graph. And then the points of intersection will be square root of 2, 2, and negative square root of 2, 2. So that's fine. Any further questions about this surjectivity stuff? Note that I can also modify this. What if I write f from r to r greater than or equal to 0, now given by x maps to x squared? Is this function surjective? Yeah, this is surjective. I have cut out all of the bad points that didn't get hit from the domain, right? I just removed, or from the codomain. I removed all the points that were not in the range from the codomain by changing the codomain in this way. Now, the picture of this function should look like this somehow. And I'm not allowed to think about horizontal lines with a negative height because those are no longer inside the codomain. And now every horizontal line with a height that corresponds to some number r greater than or equal to 0 does intersect this function. So this is surjective. Does this kind of help clarify why we made such a big fuss about functions being defined from a specified domain and to a specified codomain, and we didn't just identify functions if they had the same range, right? Like there's a property that this function has that this function doesn't have, namely this function is surjective and this function is not surjective. And that's an important property, whether or not a function has the surjectivity property. And same with the domain. Any questions on this? Okay, the definition of a bijection f from A to B is a function which is both injective and surjective. Bijections are going to be extremely important kinds of functions, which we will deal with a lot in the later chapter of this section. Okay, so there are some nice examples that I can draw up really quick, and I'm going to ask you all some questions. Let's think about this function. 1, 2, 3, A, B, C, D. A is going to map to 1, D is going to map to 1, B is going to map to 2, C is going to map to 3. What of the properties does this function have?
Surjectivity.
This is surjective. Is it injective? Not injective. Okay, let's try another one. How about A, B, C, D, and 1, 2, 3, 4. I'm going to send D to 1 and C to 2 and B to 3 and A to 4. What properties does this function have?
Surjective and injective.
Yeah, this is bijective. This is both. Let's also have an example like this, where I have something like 1, 2, 3, and A, B, C, D. I send 1 to D, and I send 2 to B, and I send 3 to A. What properties does this one have? Yeah, this is injective, but not surjective. One important point that I want to make before it's time to go is I want you to notice the following sort of ideas. If I want to make an injective function from one set to this set, and let's say that right now we're only talking about finite sets. If the codomain is a smaller set than the domain, is it possible to have an injective function?
Could you repeat that, please?
Yeah. Let's say that we're dealing with functions between finite sets. And let's say the domain is a larger set than the codomain. And that's what we see here. Is it possible for me to write an injective function from this set to this set?
No.
No, it's not possible, right? No matter what happens, I've got 4 elements and each of them must go to one of 3 elements no matter what, there's got to be some doubling up. There's no way that I can be injective when I'm mapping from a larger set to a smaller set via a function. On the other hand, yeah, so already we know that if a function is supposed to be injective, then it's got to be somehow maybe smaller than or equal to. On the other hand, if I want a function from A to B, which is surjective, is it possible to have a surjective function when the domain is a smaller set than the codomain?
No.
Again, no, right? If I have only 3 elements here and 4 elements here, using the definition of a function, each of these can only be mapped to one element of the codomain. So I'll at most have 3 elements in the range. I can't possibly have 4 elements in the range. So what we can think about is we can think about these ideas of injective or surjective functions as maybe in some way measuring the size of sets. And maybe one thing that you should think about is that a bijection, if you have a bijection, is it possible for these sets to be of different size? The answer will be no when we're talking about finite sets. And it turns out that this idea is going to generalize very powerfully. So somehow bijections should be associated with different sets of the same size somehow. That's very believable when we're dealing with finite sets, but it becomes a very powerful idea when we start dealing with infinite sets. Okay, that's about all for today. Any questions? No questions?
Thank you.
Yeah, sure, absolutely.
Thank you.
Cheat sheets on the exam. I'm kind of feeling no. Kind of feeling no.
Will the deadline for the homework be delayed so that way we can study for the midterm?
Okay, fine. Sure. We can delay the homework until Wednesday.
Cool, thank you.
I'm actually not sure about whether or not set identities will be given right now. I'm leaning towards no, but I would say that you should focus on 1.7, 1.8, 2.1, 2.2, and maybe a little bit of 2.3, but not the stuff that I talked about today. What should I repeat? One 1.7, 1.8, 2.1, 2.2, and maybe the beginning of 2.3. Okay, I'm gonna stop the recording, but I can hang out for a little bit if anyone has questions.